Section 8.5, the remainder and factor theorems. The objective here is to use remainder and factor theorems to find factors of polynomials and to solve polynomial equations. Take a look at example 1. First, we're going to determine the value of f of 3 if f of x equals the following function by using direct substitution. So let's do that first. And this turns into the following. We have 81 minus 18 minus 12 plus 5, giving us 56 for f of 3. That's part A. Now let's take a look at part B. Part B says determine the remainder if f of x, this entire polynomial, is divided by x minus 3. And what I'm going to do is I'm going to use synthetic division since the divisor is a linear binomial. So if I do that, I'm going to say, well, the c value here, right? C is just going to be 3. So I'll plug a 3 in. Along the top, I'll put my coefficients 3, negative 2, negative 4, and 5. Let me put a line so we know that this is a new line. We bring down the first one. It's 3. We'd say 3 times 3 is 9. 9 minus 2 is 7. 3 times 7 is 21. 21 minus 4 is 17. 3 times 17 is 51. 51 plus 5 gives you 56. Well, look at that. The remainder, when dividing by x minus 3, is equivalent to the value of the function when evaluated at x equals 3. So if we plug in the c value here, see this, the c value is 3. Whenever you plug in the c value in direct substitution, you'll get the same answer as the remainder using synthetic division. Let's write this as a statement now, okay? So f of c is the same thing as the remainder of f of x over x minus c. So when we take f of x and divide it by x minus c, the remainder as a result is the same thing as f of c. And what this is like a verbal statement of the remainder theorem. Okay, the remainder theorem. And sometimes we call this process synthetic substitution. Because earlier up here, this was direct substitution, where we directly plugged in the 3 to get our answer. Now we're taking that 3 and running it through the synthetic table, and we can call this synthetic substitution. Now, the following theorem is a corollary to the remainder theorem, the one that we just made a statement of a minute ago. And it says the factor theorem. The factor theorem says that the polynomial f of x has x minus c as a factor if and only if c is a root of the equation f of x equals 0, which is what we said in the last section in 8.4. Whenever we divided by something and the remainder turned out to be 0, right? When the remainder in this case turns out to be 0, we knew that the factor, or the thing we were dividing by, the divisor itself, ended up being a factor. So when you divide it by x minus c and you get 0 as a remainder, that means that x minus c is a factor. Well, in other words, if x minus c is a factor, okay, then c is a root of the equation. C is a root of the equation. Okay? So let's take a look at example 2. Example 2 says, if x plus 4 is a factor of the following, find the other factors. Then based on the factors, what are the zeros of this function? So we're going to start and say, well, if x plus 4 is a factor, then that means that c is negative 4. Right? Again, if this is a factor, then it means that this negative 4 has got to go into this evenly, meaning there shouldn't be a remainder when I do this. So I've got 1, negative 5, negative 22, and 56. I bring down the 1. This gives me negative 4, and negative 5 is negative 9. This gives me 36. 36 minus 22 is 14. And this is going to give me negative 56 plus 56 is 0. So what we know is that, remember that since this goes in evenly, since the remainder is 0, the resulting equation, or the resulting polynomial that we've been looking at, right, this was x to the third, so this is really x squared now, minus 9x plus 14. We know that this is a factor as well. So one of the factors is clearly x plus 4 from the beginning that was stated, and there's the other factor. So this means that the function can be factored into these two factors. Well, can we factor this even further? Yes, we can. Let's go ahead and do that. So what numbers multiply to 14? 7 and 2, and 7 and 2 definitely give you 9. If we have them both minus 7 and minus 2, we end up getting the negative 9, which is what we're looking for. So given one of the factors, x plus 4, we can say that right away if we plug in negative 4, the c value, we'll get a 0 remainder, which gives us another factor of the original function. So this was one of the factors of the function, this is the other, but this factor breaks into these two. So as a result, this is the function when it's factored. Okay, that cubic function we looked at a moment ago in its factored form. Well, that means that x equals negative 4 is a root, x equals 7 is a root, and x equals 2 is a root. And how do we know that? To find the roots, or the zeros of the function, we set the function equal to 0. This is also giving us the x-intercepts. These are the x-intercepts. Example 3 says, if x equals 1 is a root of the following equation, find the other roots. Well, now we're given a root. We're not given a factor. If this is a root of the equation, it means that one of the factors is clearly going to be x minus 1. And then we're going to have two other factors. Okay, already, if I have a root, I know a factor. Remember, this is x equals c, so c is 1. So x minus c is one of our factors always, right? Because if you were to set this equal to 0, you make a t-chart, you get x equals 1. That's that. So if this is one of the factors, then I know right away if I plug a 1 in on the outside, and I run it through my function here, I'll get 0 as a remainder for sure in this spot, so I can then have a quadratic to get the other two factors. So we'll start by bringing down our 1 here. 1 times 1 is 1. 1 minus 4 is negative 3. This multiplies to negative 3. Negative 3 minus 15 is going to be negative 18. This multiplies to give us negative 18. Negative 18 and 18 is indeed 0. So we get a quadratic as a result. We can actually call this the depressed equation. Not like sad or anything. Depressed meaning the equation as a result of the synthetic operation that we just performed. So we're told that this is our result, so now we can factor it. Let's figure out how to factor this. Well, we're going to say right away it's going to be x minus 6, x plus 3. Well, if those are the other two factors, the question said to figure out the other roots of the equation. So this is the depressed equation. So this is going to give us a root of 6 and a root of negative 3. So these are the other two roots. The original root was x equals 1. Example 4 says to determine if it is a factor. Well, to see if something is a factor or not, again, we just run it through the table. So if x plus 2 is the factor, and then the value we're going to run through is a negative 2 here. It's going to give us negative 4, and negative 4 is negative 8. It's going to give us 16 and 1 is 17. Negative 34 and 7 is negative 27. And since the remainder is not equal to 0 here, then x plus 2 is not a factor. It's not a factor. But we do know this. We know that the evaluation f of negative 2 is equal to negative 27. Okay, is equal to negative 27. Which is also a way of saying that this is like your x coordinate and this is your y coordinate. So remember that the remainder is really the y coordinate if we're trying to plug in x equals 2 into this, say it were a function, okay? If it were a function, I know it's not, but say it were a function, if we wanted to figure out f of negative 2, f of negative 2 would be negative 27. But again, it's not going to be a factor. Only when the remainder is 0 do we have a factor as a result, or a root that's being plugged in. And two other theorems that we should know, that every polynomial equation with positive degree n has exactly n roots. And we've talked about that already. So that means that if something is x to the third or x to the fourth or x to the fifth, there's got to be 2 or 3 or 4 or 5 roots. Now, the other thing to note is that if a polynomial equation has real coefficients, then if it has a plus bi as a root, it must also have a minus bi as a root. And this is because they're complex conjugates, and you always get that plus or minus.